Now, I don't know about you, but these days I'm using AI in my everyday life quite a lot, like to help me create art, write code, write formal letters, ask questions, brainstorm, all kinds of stuff. And, that's only really been possible very recently. I think AI researchers, we're pretty privileged to be in this time in human history and see these improvements happening in real time. Um, and we've seen how quickly they evolve, but I still think there's a lot left to do. I think we can expect still more large improvements even in, the near future and next few years. And we've seen that even in the last months, right, with O1, R1, and so on, big improvements in various benchmarks in reasoning. Um, and after all, that, it's a very young field overall, but like, that subfield uh, with learning chain of thought, I mean, chain of thought itself is only really from 2022. So yeah, I think it's really impressive how fast things are moving. So in the context of this talk, I'm going to be talking about methods for self-improving language models, and that means getting better at tasks. In particular, that will mean that they're getting better at reasoning so that they can get better at those tasks. Uh, so for an AI to train itself, I mean, that means it needs to do this introspection as it's training. So normal sort of classical training was like this fixed data set and it would sort of learn from it. But that's kind of moving now a little bit where, in like reinforcement learning setups, and particularly with reinforcement learning from AI feedback, models are sort of like training themselves in a much more sophisticated way. For example, we can imagine models that create new challenges, tasks to train themselves on. They can evaluate themselves whether they're getting them right. So we call that self-rewarding, and then update themselves based on what they've understood. So that means then they're going to be getting more knowledge, more reasoning ability. And so a research question is, can they do this kind of training on themselves? And can that help them become superhuman? So I have a picture down here of one particular approach for that. That's called self-rewarding language models, which I'm going to be talking about a bit later. But in terms of reasoning, when we're doing this kind of self-improving, you can look at this as like two different ways of improving reasoning. So these are called system one and system two sometimes by people. So system one, like in humans, we would see that as reactive and relies on associations. And in machine learning models or LLMs, it can be the same thing. So you can think of the transformer itself, so like the neural network, as this kind of performing this system one reasoning. So where you have this hidden states in the neural network that's going through a whole bunch of multiplications, attentions, and so on. That it can be seen as your system one reasoning. So in that case, you have a fixed compute per token. You're directly outputting the answer. But there's some problems with LLMs as we have them now. In particular, they can learn spurious unwanted correlations. There's hallucination, sycophancy, jailbreaking, and I'm gonna show some of those things later. And then you can try and fix this stuff with what's called system two. So that's more deliberate and effortful thinking. And the most common way we think of that system two today is by generating like language tokens that are a chain of thought. So now that's not just, the pushing these numbers through the neural net. You're actually looking at the tokens the neural net outputs as a thought stream before the final tokens that will be the final response. Now, what's powerful when you do that is that system two chain of thought reasoning can actually do a whole bunch of stuff like planning, search, verification, various kinds of reasoning, even though it's generating sort of auto-regressively, left to right, it could still potentially do all that kind of sets of thoughts, as you'll see models like DeepSeek o1, 3 can do. So yeah, so those are the two kinds of things that we can effectively improve in. Try and improve like the architecture or the weights of the model and improve system one, or try and improve how it generates these chains of thought or other ways of doing system two before it outputs a response. I mean, obviously they're related because it's the same language model doing both things, but so that's the goal. Try and do this self-learning to improve these things. First, I'm going to go through some history of how we got where we are like today, and then talk about more recent works from the last year or so after I go through this history. But before, we're going to start pre-2020 to prehistory, if you like. So language modeling itself, that goes way back. I mean, yeah, Claude Shannon in 1950s talked about that. So it's about taking language and predicting the next token or the next word at each step. And obviously that's the pre-training mechanism we use for large language models, and that's how they get their name, where you're just trying to predict the probability of these tokens. We do this now on these massive corpora and pick up those probability distributions. So in 2003, there's sort of one of the first methods for doing that with a neural network. That's Benjio, Ducharme, and Vincent. So they had word embeddings at the first layer, and then various layers, 10H and softmax, to get the final prediction. And I just put an interesting quote there in their conclusions that they say there's probably a lot more to be done to improve the model, the architecture, computational efficiency, and they'd like to increase the capacity without increasing training time because they want to deal with corpora of hundreds of millions of words. So, that's kind of where we got to some years later. Now, that was 2003. Most of the 2000s, actually, the research wasn't really focused on neural networks. It was focused on support vector machines. So, these kernel classifiers. I worked in that area too. As you can see, there's a paper from me. And, it was kind of that, well, held back the LLM story, at least for a few years. So here I have a slide from myself, Renaud Colobert, from 2008, presented ICML, where we were trying to argue that the support vector machines of the day, they were used in these cascades of systems, parse-to-speech taggers and named entity recognizers and parsers, and it's not a good idea because we could train the whole thing end-to-end with a neural network. And, no one was really doing that then. So we had a paper at that time, Unified Architecture for NLP, which we considered sort of the as a successor to the Benjio work from 2003 there. So here, what we did was we also had a neural network with word embeddings at the first layer, then convolutional layers, max over time, which is a kind of proto-attention, and followed by a softmax. And we showed that you could train this model as a sort of mass language model on something like Wikipedia, which actually was pretty tricky at the time with the compute we had, and it could learn some pretty interesting things, like you could see from the word similarities. This is obviously pre-Word2Vec, which I think was 2013, which is a simpler model, right? This is a more complex neural net, that you could do that. So you could pre-train on Wikipedia, and then afterwards you could fine-tune on tasks of interest, like part-speech tagging, named entity, chunking, SRL, and that worked. So yeah, this was a predecessor to where we are today as well. It was interesting because at the time that wasn't appreciated by everyone in the NLP community. So in the Stanford Natural Language Group, they had reading group there where they called it a bullshit ICML paper that was kind of on their public website. And then this same paper won a Test of Time award at ICML 2018. And then, Stanford University then opened this Center for Research on Foundation Models, and their position paper called that same paper Prescient Work. So we kind of went from bullshit to prescient in that number of years, and that's kind of how the field changed. Of course, these papers I've talked about, just a few papers. There's many papers, right? They all build on each other. I don't like to think of, kind of like one paper that was the paper that did something, because they're all this work builds on top of the brilliant work before. But so I just show a few here of a timeline though, of how these things went. Yeah, the interesting thing is of how fast the use of neural nets in NLP and machine learning grew. From this time, from say 2008 to 2018. So there was like 4 papers in ICML 2008 with the words deep or neural in them, and I'm sort of co-author on 2 of them, and then there's like 100 in ICML 2018. Obviously, this is a neural network-based things are the majority today. That's the paradigm of today. Of course, can't say what's going to be in the future, but it's looking like a pretty powerful approach. Yeah, so of course we were interested in pushing this further and making these models reason. So in 2015, we devised this set of tasks, very simple tasks called the baby tasks, which ask these simple questions given little stories. But the neural nets of the day, LSTMs, actually couldn't solve them. And so we were hoping that they could sort of spark innovation of new methods. Around the same time, the LLM attention mechanism was born in 2014. So the Badenow-Cho-Bengio paper. So that was built for machine translation, where you'd have a tension between the target sentence words and the source sentence words, so that you could have an alignment between the words in the 2 languages, so you could translate them. And you can see this sort of attention map picture in the middle of the slide here. So yeah, what we showed was that for these kind of baby reasoning tasks, if we stack these layers of attention, then you could actually do multiple reasoning steps. So if you've got a question like, where is John here? So Daniel went to the bathroom, Mary traveled to the hallway, John went to the bedroom, John traveled to the bathroom, where Mary went to the office, where is John? Then you could attend to these correct sentences to get that right. Actually, that one's pretty easy because you only need to attend to John traveled to the bathroom, the last sentence. But then that's called one supporting fact question. But then you have a 2 supporting fact question where it's a little trickier. So there, John dropped the milk, John took the milk there, Sandra went back to the bathroom, John moved to the hallway, Mary went back to the bedroom, and the question is, where is the milk? So now you have to see that the model will attend on like the first 2 layers. You can see the attention scores here in hop 1, hop 2, hop 3. This is in the story 2 supporting facts. You see it attends to the sentence, John took the milk there. And so now it knows that John has the milk. And then it can attend to this next sentence, John moved to the hallway, in the further layers of the neural network, so that it can answer the hallway is the correct answer. So this was basically showing how, in these very simple problems, the tension mechanism, when stacked layer by layer, can give you more sophisticated reasoning. And so this was built into this neural network at the time called a memory network. So it had these stacked layers of attention, query and key embeddings, position embeddings, so it knew which sentence or token was being attended to, neural networks between attention layers and a final softmax layer. And so in many ways, it was a kind of predecessor to the transformer, which improved on this recipe with some other things like multi-head attention, self-attention, and normalization. And yeah, that led us to 2017 with the advent of the transformer. And that's kind of more or less the architecture we're using today with some tweaks. And then BERT in 2018 showed that, a masked language model with a transformer could work very well. Yeah, I just want to link that to a paper from 2014 with Sp25, Vinyals, and Quarkler, which was showing that you could do sequence-to-sequence learning with neural networks. Now, I think that wasn't with attention attention maps yet, but still, the conclusions from that paper were essentially the scaling hypothesis that we're using today. So you can see this conclusion slide. If you have a large, big data set and you train a very big neural network, then success is guaranteed. It's a little bit glib, but yeah, this scaling hypothesis, essentially when Ilya Sutskever went to OpenAI, they drove this hypothesis, making GPT-2, GPT-1, 2, 3, 4, and so on, right? These bigger models, more data, and indeed this has worked. So these are basically the ingredients that have taken us to some degree, sort of LLMs everywhere. So I asked actually an LLM to give me a list of LLMs that have come out in year order. So this doesn't include all of them, but you can see a bunch that have come out here. But that's just so far been about mostly about language modeling and the language model objective function, and that isn't actually enough. So we do need other ways of training these models, and I would characterize sort of 2020 onwards as exploring that more deeply. Now we have these better language models. So 2019, actually, we did a work on dialogue agents, which we call the self-feeding chatbot, where they could train not only just with this sort of language model objective, but by using a reward model. So we train a reward model, and then during conversations with humans, if it thinks there's a large reward for one of the things it said, it can add that back into the training set and then do supervised fine-tuning on this ever-growing data set. So this was kind of a pretty simple version of what's being done today with sort of, RL, HF and RL AIF. Then in 2020, we released this BlenderBot model that was a pre-trained language model up to about 10 billion parameters. And then crucially, we don't just use the language model pre-training as objective. We supervised fine-tune that on dialogue data, which was human annotated. And then when you you evaluated this with humans, they actually said our best models were about as engaging as the average human and superior to another model from Google called Mean at the time. But the actual recipes that we use today, we do use supervised fine-tuning today, but there's some more sophisticated stuff as well, right? So in 2022, you had the Instruct GPT paper, which advocated more for reinforcement learning from human feedback. So what you do there is you have this sort of SFT stage where you collect demonstration data from humans. That's step one. But step two, you also collect comparison data. So which of these two responses is better, A or B? And then get humans to rank those. And then you train a reward model So similar to how we had a reward model in the self-feeding chatbot. But then you use reinforcement learning with that reward model to then kind of generalize those comparisons with the reward model function to new generations from your policy, and try and make your model better by it generating responses and essentially judging with this reward model and fixing itself, right? So that's kind of more of a step towards this self-training kind of goal beyond the language model training criterion. And then there's sort of an alternative to RLHF. Well, it's a little bit simpler, called direct preference optimization. I mentioned because it's also pretty popular, DPO. So it sort of says, okay, let's not use a reward model if we've got preference data. We're just going to directly push the probability of the chosen in a preference pair sort of up, and the probability of the rejected in the preference pair. So these would be two possible outputs from the model: push one up, push one down. So there's a sort of a margin between the two. In certain experiments, DPO works quite well compared to PPO, RLHF, and then SFT can also work, but generally a little worse. But it depends kind of on the setting, and I think in some cases you really do need the full reinforcement learning, because your policy is going to change, right? So the DPO, just with a fixed preference data like that, can't take that into account. But we'll see ways of fixing that by making it iterative as well. But overall, you choose one of those methods: SFT, RLHF, or DPO, and fine-tune your language model with one of them, and then you get pretty good instruction following. So there isn't necessarily sort of this explicit chain of thought reasoning yet, but compared to the original language models, you're doing really well. So for example, here, this is from the Instruct GPT paper. You've got this prompt: what's the purpose of this this code? GPT-3, without the sort of fine tuning, doesn't do a very good job, or Instruct GPT does a much better job on the right-hand side. So obviously, yeah, today we all know quite a lot about using these ChatGPT type models, as we're mostly, yeah, a lot of the population is using them at this stage. So, okay, that got me up to basically having a really good system one model, right? It takes in this input, say this instruction, it directly spits out an output, but it isn't doing the system two reasoning. So that's kind of the next step. And yeah, between say 2022 and 2023, the approach to doing that was what I would call a prompting approach. And so I'm going to talk about those first, and then we're going to look at more modern things from the last year or so, where we're going to more train directly to do this system two reasoning instead. So chain of thought prompting, the initial papers, they did that in a couple of ways. One was by what's called few-shot prompting. You would have, say, for some maths task, you would have examples of the kind of chain of thought reasoning you would like to see. So you say if you had, I don't know, 8-shot examples, you'd have 8 examples of doing reasoning. So it can be, that's shown here, with the, instead of just saying the answer is 11, as in standard prompting, you would have: Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls, 5 plus 6 equals 11, the answer is 11, right? So that's the chain of thought there that's highlighted. So you'd have examples of that in the prompt, and now you would generate from the language model, and it's going to mimic that few-shot prompting and use a chain of thought. And so that was kind of one of the first approaches of prompting. And then in the other paper here, large language models are zero-shot reasoners. They showed actually you can be even simpler. You could just say, let's think step by step in the prompt, and that could still bring about these steps or these chains of thought could happen that it could generate before it generates the final response. And you get really big improvements on math tasks. So, you could go from, say, 10% on GSM-8K up to 40 or 50%. So, yeah, that's kind of really spurred people to push the system two approaches further. And, it's not just math tasks that works for. So, you can also look at the other failures of system one of the base language model. It also has a factuality and hallucination issues, right? So here's an example query, name some politicians who were born in New York. And the third one it lists here, I think this is from ChatGPT, is Michael Bloomberg, which is incorrect. So you can try and set up a system two reasoning type chain of thought to fix this problem. So it's not a math problem, right? So that's a paper we did called Chain of Verification, where the idea is you get this first baseline response. You can think of that now as your draft. So it's not actually your final response. It's part of your chain of thought. And then given that draft, the language model asks itself more questions to sort of check its own draft. So it could ask, where was Hillary Clinton born? Where was Donald Trump born? Where was Michael Bloomberg born? And then answer those again as single questions. Now, the answer might be different than sort of writing out this whole list from the name some politicians question, because it's sort of phrased differently. You actually get a different response from the model. And models tend to be better actually at these single question answer pairs that are short compared to these long kind of responses they write. They're more likely to get something wrong somewhere in the long response. So when you plan those verifications of those verification questions and execute them, you can actually get the model to see its own discrepancy. So now it actually knows that Michael Bloomberg was born in Boston, even though it's included him in the list of politicians who were born in New York. And now you can make it kind of cross-check itself and see that it was wrong and write a final verified response and treat the old one as a draft. And now it gets that correct. So that's kind of a somewhat different chain of thought system two reasoning compared to the math problems. And yeah, in that work we showed that on various knowledge tasks you can get large performance in precision, like 3 times as good with that approach. So yeah, I mean, and you could think, oh, that's sort of maybe because that paper was from a little while ago, that it might be fixed today, but actually I tried on ChatGPT 4.0 and it's still making these kind of mistakes. Like here I did a query, list 30 most famous women in AI, and it included Joshua Bengio in the list, or what prominent women work at OpenAI, and it said Ilya Sutskever as the first in the list. So still something that definitely needs to be fixed, and you can fix it with this sort of system two reasoning. I think actually 0.1 does better, but yeah. Yeah, and there's other things you can do with this system two reasoning as well. So here's another problem with language models, that they have what's called semantic leakage and sycophancy. So when you do attention, because it's a soft attention, it's not sharp. You're assigning probabilities across the context. So there'll be all these sort of non-zero values, and it means the whole context can affect the LLM output. And this can be bad because even basically we see irrelevant parts which look sort of superficially correlated tend to have an effect. So, for example, a prompt like "he likes ants, his favorite food is" can get completed by the language model as "ant covered chocolate," which isn't particularly desirable. "He likes yellow, he works as a school bus driver." That's from Ganon et al. In 24. It's sort of, I see this as a similar problem, the sycophancy problem. If you say something like, as an instruction, "I think that the sun is yellow when viewed from space, what do you think?" So you kind of prime with the wrong answer, because actually that's an illusion caused by atmosphere. Then it will actually agree. The LLM tends to agree with you and say, yes, the sun is actually yellow when viewed from space. So I sort of see that as a similar problem, that basically you've got that text in the context and it tends to attend to it and get things wrong. So another example, if you add some facts about some city in the context, like Sunnyvale, and then you ask for someone's birthplace, it's likely to say Sunnyvale as the answer. Yeah, I just typed in this one today. Did OpenAI have a model called self-feeding at one time? And ChatGPT 4.0 replied, yes, OpenAI introduced the concepts of self-feeding in the self-feeding chatbot paper, which, that wasn't actually from OpenAI, that was from Facebook AI research. So again, you can still prime these, this is a sort of current day problem. So how can you fix that with System 2 reasoning? So there was a paper called System 2 Attention we did last, that was end of 2023, I think, where you do this chain of thought reasoning, which attempts to rewrite the original instruction and remove the bias. So again, this is done by prompting. So essentially the prompt is to give the original instruction and then ask the language model, rewrite this instruction, remove the irrelevant parts and the bias, and then you'll get a new instruction, and then you get the language model to answer the rewritten instruction, right? So you want to get rid of this bias, and then you can get better results. You're not biased as much by this issue. So for example, "I think the sun is yellow when viewed from space. What do you think?" When you use this sort of chain of thought System 2 Attention to rewrite that, it would rewrite it as, "I'm curious about the color of the sun when viewed from space. Can you provide information on this topic?" So to remove the yellow, which was kind of, biasing the question to a certain answer. And yeah, this works also on math problems. If there's like, say, there's parts of the math problem which are completely irrelevant. They can actually fool a model, and it will try and remove those. So yeah, this is just to show you really that chain of thought and System 2 reasoning, it's not just for math problems. There's like a lot of things a model can think about with these intermediate tokens and fix a lot of problems in all kinds of tasks that it's trying to solve. This last one I show, it's the task with evaluation. So you're given a question, like an instruction, and two possible responses. You want the model to say which of the two responses is better, which is a really important thing for training, as we showed, because you could basically use that as a reward model. And it's also important for evaluation as well. But yeah, you can also do System 2 reasoning there. So in this paper, branch, solve, merge, the way that was done was, again, through prompting, by asking, given that instruction, to first ask the language model to break down its evaluation into different criteria, such as relevance, clarity, accuracy, originality, and it would come up with those criteria specific to the task that it's trying to solve, and then to generate an evaluation independently for each of those different branches. And then merge them back together again. And it was shown that that could give better evaluation results through the extra thinking time, basically, that the language model has. So yeah, that was, there's many other works as well during that period, but I just wanted to kind of give an overview of a few of them to show there was a lot of prompting approaches that showed that spending time thinking could get you better results. But what we really want to do is try and train these models, end to end, to be able to be good at reasoning, not like just prompting, right? So that I'd say the next wave after that is, and we're in it right now, is improving this reasoning through optimization. And so better reasoning via self-improvement. And to get there, I'm going to start with the self-rewarding language models that I was talking about right at the beginning of the talk. So this is a method where the LLM improves itself by assigning rewards to its own outputs and optimizing itself. So yeah, where the hope is that this could lead to it becoming, smarter at each iteration. And yeah, so the sort of the research question is, can that make it superhuman? So the standard reinforcement learning from human feedback, which I mentioned earlier in the talk, uses humans in the loop. First, to create the supervised fine-tuning data, so the instructions and the responses, and then to collect these judgments, so which of these two responses is better, A or B. Now, yeah, that's shown in this picture that I showed before. So there's two spots where there's a human, and the problem is language models are getting better and better, right? So it's just getting a really tricky job for humans to be as good as we need for these tasks. Humans need to read these responses really carefully in order to make decisions. So, for example, now that our LLMs are really good at writing code, or I don't know, sophisticated math outputs, even getting good at, like, I mean, maybe not perfect yet, but getting good at legal or medical outputs, things like this. The problem is it's harder and harder for humans to be good labelers for these tasks, right? You might need some of the best mathematicians human mathematicians in the world, right, to label whether these responses are correct or not, right? And similarly, you need really good coders, or even if you don't need them today, you'll certainly need them tomorrow, right? And so the average sort of human that you pick from the population, then they're just not going to be good enough at these specialized tasks and be able to annotate this data. So this is what motivates trying to get the language model to try and help itself. And so that's basically, otherwise, how can we continue improving a model if it's already, fairly superhuman compared to the average human that you could pick? So there's two observations that can help us solve this. Observation one is that we know language models can continue improving if they're given good judgments on response quality, because that's what was shown in reinforcement learning from human feedback, or in something like DPO as well, right? So if you have good preferences of chosen and rejected pairs, then you can improve the model by training and pushing up the probability of the chosens and down the probability of the rejecteds. And the same thing for a reward model with reinforcement learning. And observation two is that we actually have now language models that can provide good judgments on model generation. So I was showing you the branch solve merge approach just earlier. So that's an approach for a language model, basically to give a judgment on two responses as an instruction following task. So this is called LLM as a judge, typically, where for the language model, it's not any different a task than all the other instruction following tasks it has to do, like write some code or respond to this particular question. And in particular, this question we're asking is which of these two responses better, A or B? So, and there's a bunch of work showing LLM as a judge is actually a pretty good method. So how about combining these two things together, right? So we replace the human feedback with the LLM feedback. So the key idea then is to train this so-called self-rewarding language model. It's going to be its own judge as it's training. So it needs to have this instruction following capability for all the kinds of user instructions we want. But one of those user instructions is actually the evaluation task that we're interested in. So it looks like this. Here's an instruction. Here is a model response. And then the task is, can you assign a score, say between 0 and 5, or there'd be other ways of doing that as well, but to this response, and then based on some rubric. And then you would expect, say, a chain of thought reasoning process, and then a final judgment of the score of the response. So if we have these two things, then we can make this model train itself and be self-rewarding. So we also go through an iterative process of data creation and curation so that we close this whole training loop where we train on this new data. And then the goal is the model is going to get better in terms of both instruction following and evaluation ability in each cycle. And we empirically showed that that was possible. So this was right at the beginning of last year. So that was the picture that I was showing right at the beginning of the talk. So yeah, we did these experiments on Llama 270B. And we used Open Assistant as a sort of seed. So that's seed instruction data. And it also has some seed evaluation data. So the LLM as a judge prompt that we use looks like this. So that's asking it to do chain of thought and then score out of 5 a particular instruction. And then we're going to go through this training loop. So the first part is it's going to generate new tasks. So we use something called self-instruct to do that. So basically, you start with your seed instructions, which are from humans, and you use few-shot prompting with a few of those instructions to ask the language model to generate a new instruction. Okay, and then you can do this, hundreds of thousands of times to get a whole new set of tasks. Then for those tasks, you can generate responses. So you'll generate multiple candidate responses for each prompt or task. So let's say 4 in our case. And then you generate rewards with the LLM as a judge prompt that I just showed to give you those scores for each of the 4 responses. And from that, you can generate preference pairs. So you take the highest scoring of the 4 responses, and that would be the chosen for DPO, and the lowest scoring would be the rejected. You can carry on training your model now with this DPO training, and then repeat the whole cycle. Now you have a better model, MT+1. You can go back, generate new prompts, generate new responses, generate new rewards, and so on. And we do this loop like 3 times in the experiments in that paper. And we're going to evaluate the performance on 2 axes, the ability to follow instructions and its ability as a reward model. There's some benchmarks called Alpaca Eval 2 and MT Bench at the time that we used, and another test set of prompts. And we use GPT-4 evaluation and human evaluation to check how this model performed through the 3 iterations of self-rewarding. And you can see that they agree with each other, humans and GPT-4, that we compare it to doing supervised fine-tuning on each iteration, the model's getting better. So it's getting better than the SFT baseline. And yeah, so that's the sort of power of this self-training. And we can look at the win rate on Alpaca Eval 2. And this paper got quite a bit of attention at the time because this win rate for such a sort of simple model was quite good. It started from this Llama 70B, and the win rate went up from 10% to 15% to 20% in the 3 iterations, which put it almost on par with GPT, a version of GPT-4. And, this was kind of just done by the first author is Weizhe Yuan, who's a PhD student at NYU. So there wasn't like a big team building this project, but the algorithm it works quite well. Yeah, so you could look at what it's actually improving at, and it does improve on all kinds of skills, but particularly more things like humanities, extraction, STEM, role play and writing, more than it improves at, say, something like math, code, and reasoning. And the reason why that would be is because the LLM as a judge might not be as good at evaluating math, code, and reasoning, and so it's harder for it to improve on those. This is a breakdown, of these topics. You can see that the gap between the iterations is smaller for things like math, which is on the far right. And then you can measure the ability of this model as an evaluator. And you could, one way of measuring that is by looking at its correlation with human judgments. So the pairwise accuracy, we had a whole bunch of metrics, but the pairwise accuracy metric would show its agreement with humans on whether A or B are the right way around or the wrong way around. And you can see that it does increase, not by a massive amount, but it does increase over the 3 iterations. So it is actually getting better at being a reward model, which I think is exciting because if the model is getting better at making judgments of what's right or wrong, then it's getting better at rewarding itself following instructions. So there's kind of a virtuous circle going on there to some extent. Of course, it plateaus in experiments, but it still gives it the capacity to self-train and get better than the initial human annotations that it had at the beginning. Now, as I said, it didn't improve as much on reasoning tasks. So the next thing we wanted to ask was, how can we make it improve on those? And so in April of last year, we did this work called iterative reasoning preference optimization, which I can see from the picture, it's a similar pipeline, but now we're going to generate chain of thoughts. So in the experiments I just showed you, there were no chain of thoughts, right? It was just kind of a system 1 language model output the answers for instruction following. But in this version, we're going to generate chain of thoughts and then answers, and we're going to compute rewards, and otherwise the pipeline is the same. Now, the rewards aren't going to be done by LLM as a judge because we don't trust the LLM on these math tasks as much. I mean, I think that's a subject of research. How, can we get them to improve by trusting their own judgments? But in this work, we just said, okay, we've got a bunch of math training data where we know the right answer. So let's just use that as a reward. And this is being commonly called in the last weeks is like a verifiable reward for a math problem, right? So what we're going to do is we're going to generate the chain of thought and then the final answer, and then we're going to extract the final answer from the LLM response. So sort of remove the chain of thought part, just get the final answer, and then just do a match with the answer that we know for the math problem. So you can do that with this kind of prompt. So where you give the LLM the prompt, your task is to answer the question below, give step-by-step reasoning, and when you're ready, please use the format final answer : So then you can just simply do this, heuristic extraction where you search for final answer : grab the text afterwards. That should be your answer, and now just do a string match. or some other fairly simple match with the answer, the known gold answer. And that's how you can build your DPO pairs and improve your model, and then again iterate round. And that's the iteration again is important, because now we've got a better model answering these math problems. We're going to generate new chain of thoughts with the better model, compute the rewards, and go around in a loop. And we showed on math problems like GSM-8K that that's working really well. So yeah, you can see these improvements across iteration 1 to 4. It's gaining a little bit less than 10% there, and also improves on some multi-choice problems on Arc Challenge and on these harder math problems as well. And yeah, we just showed that the DPO training is really important. You can't just use supervised fine-tuning. With this training, you really need the negative examples to be pushed down. Otherwise, it doesn't work. And yeah, so in 2024, September or so, OpenAI's O1 came out. Of course, the exact method is unknown. They didn't, publish a paper about it, but they did have, well, they didn't even show the chain of thoughts either, right? From the model, there was a summary of the chain of thoughts. I think they still do that, but it was capable of answering some quite sophisticated reasoning math problems. And everyone was wondering, how did they do it? Did they use some kind of process reward model that was like evaluating the in-between steps? Did they use MCTS or some really sophisticated search mechanisms to train with reinforcement learning? Or, a lot of ideas were posted on Twitter of how they do this. And then DeepSeek R1 came out just this January, and Mark Chen from OpenAI tweeted, "Congrats to DeepSeek on producing O1 level reasoning model. Their research paper demonstrates they've independently found some of the core ideas that we did on our way to O1." Okay, so then that means, assuming that OpenAI used the same stuff as DeepSeek, we have a DeepSeek paper, so we can look at what they did. And in some respects, it's quite similar to the iterative reasoning preference optimization that we did earlier in 2024 that I just showed you. So they have a prompt which asks it to think and then to put the answer in a box. You see this answer here in the prompt, and then they extract that, and then they use a rule-based verification of correctness with verifiable rewards, and they apply that in a loop, generating chain of thoughts, checking just the correctness of the answer, and then rewarding this correctness. These are a different optimization technique. They don't use iterative DPO, they use GRPO. But otherwise, this recipe looks kind of like that. It's just done much bigger scale. So in the experiments I showed you, we just had like one data set, like GSM-8K. So key here is start from a really strong big model. I think it's a 600 and something parameter model, right? 671 billion parameter model, DeepSeek 3, and then you have a large amount of this reasoning data with verifiable rewards, and you train with this RL generating chain of thoughts and rewarding the ones that it gets right, and basically exploring the space of chain of thoughts. And they observe that the chain of thoughts get longer over training as it finds sort of more sophisticated reasoning techniques. And then the final model does very well on these code and math problems, similar to OpenAI's O1 model. This actually was a big news outside of AI. You can see that NVIDIA's these articles here on Bloomberg. NVIDIA's DeepSeek drop has Wall Street fixated, and with their stock plunging and stuff like that. So it was a surprisingly big splash. And then, yeah, I have a couple of examples here of the chain of thoughts that it does. The one on the left is from their paper. It's generating this answer to this question. And then in the middle of it, like the chain of thought, it says, wait, 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 that's an aha moment I can flag here. Let's reevaluate this. And it starts saying some other stuff. So they were just showing how it learns to rethink and, fix its own mistakes. And that was all done just with this this training that just rewarding the final answer and it was doing the rest itself. And I personally love the simplicity of it, that we didn't have to do, really complicated things in the middle. It's just, just rewarding the end, and you can already get these impressive results. So the one on the right is kind of a more funny one. Ask DeepSeek to select a random number, and it outputs this large amount of chain of thought where it sort of overthinks itself. Maybe I should go with something like 7777, but that's 4 sevens, which might be too obvious. Alternatively, 1, 2, 3, 2 sequential. Well, I bet if I close my eyes and 42, wait, no, that's from Hitchhiker's Guide, and so on. So it's pretty amusing what it ends up doing. But yeah, almost a little human in a way though. But I don't think that's actually the way we really want to generate random numbers, obviously. Yeah, so from my own team's work, before that came out, so 2024 October, we were looking to extend our chain of thought training results from iterative reasoning preference optimization. We showed that work quite well with math problems, but we want chain of thought reasoning for all problems, right? Like even if you're, I don't know, thinking about how to write a poem, you might, do a whole bunch of thinking, write some drafts, try and understand what you're going to write about before you actually write it. Just to pick an example that's very different to math. So we try to follow the same recipe. So we have a prompt, a generic prompt just to initialize the model, and we ask it to respond to whatever generic query, but do it in a comprehensive and detailed way by writing your internal thoughts. And then you must include this draft response in its evaluation. And after you write your final response, have this special tag. So again, that's so we can extract the response out and separate it from the thoughts. And this is the same trick that we did before, right? And the same trick that DeepSeek does. But here we're going to do it not on math problems, but on all kinds of other instruction following problems. But now we won't have a verifiable reward anymore, but we still have these LLM as a judge, right, that we were using in self-rewarding. So we can use that on the response to judge whether the response is good. But the difference between this and the original self-rewarding work is that we have the chain of thought generation before it. So we tried this and actually ended up working quite well. It gave gains on this Alpaca eval and another benchmark called Arena Hard. It's actually third on the Alpaca eval leaderboard, I think, at the time, and it was the best 8 billion parameter model on Arena Hard. I think one interesting thing about the training, so again, we're doing this iterative training with DPO, is that, so this is called thought preference optimization, TPO, and we compare it to the direct baseline in this graph in the bottom right, which is basically no chain of thought. And you can see in the first iterations, TPO actually makes the model a lot worse. And that's because these language models, so we're using like Llama 3, 8 billion, they're already really well fine-tuned to be good without the chain of thought, right? So that kind of had a massive advantage over trying to make it do the chain of thought. But after we train it on successful chain of thought outcomes using the LLM as a judge or the reward model, then you can see that the gap closes and then it starts improving on iteration 3 and 4, and now it's better than the direct baseline. So yeah, so I think this was really promising because it showed you could do this chain of thought training, not just for math problems or verifiable tasks, but for anything, right? And yeah, so here's a couple of examples of things it does. Yeah, is so you can, say for a query, write me a poem, or what dog breed is smallest. It's going to do a whole bunch of thinking, like draft responses and evaluation, or various thought processes before it gets the output. Yeah, and then DeepSeek R1 in their paper, not 100% sure if it's doing something the same as what we're doing there with TPO, but there's a hint it is, because it says here, I highlighted it, for general data, we resort to reward models to capture human preferences in complex and nuanced scenarios. So I think they're also generating chain of thought and then doing that, but it wasn't like fully spelled out in their paper, so it wasn't completely clear. Yeah, and then there's other things we can do. So these, as far to my knowledge, aren't actually yet in these bigger models. So these are more just like research papers that hopefully then get scaled up to these bigger models. The next work we did to try to show that the language model, so far we've shown it's quite good at improving its instruction and reasoning ability, but we also want to explicitly improve its ability to evaluate itself. Because if we can do that, then when it's doing these judgments, it's doing these reward model judgments, it's going to get better at everything, right? It's going to get better at instruction following as well. So this work is called meta-rewarding language models, where it's going to try to improve its own judgments by meta-judging its judgments. So obviously a little bit meta, this work. But so yeah, now you can sort of see the language model in 3 roles: as an actor, so following instructions; as a judge, judging responses to those instructions; and as a meta judge, it's going to judge its own judgments. And I'll show you how you can do that. We call that LLM as a meta judge. So there's a prompt for that. So you'd have a given instruction from the user, a response from, say, a model, and then judgment A and judgment B, which could include the chain of thought and the final verdict. And then you want the language model to judge which of the judgments is better, A or B. Now we have a particular algorithm then for like basically taking all different judgments, calculating the meta judgments, and then the ELO score amongst them. But the reason to do that is to create preference pairs amongst judgments. So now we can say, okay, this judgment looks better than that judgment because our meta judge tend to say that. And so we can construct preference pairs, again with DPO, of which judgments are better. So now we've got 2 types of preference pairs. The ones we had before, which were like response chosen is better than response rejected. But now we also have judgment chosen is better than judgment rejected. And we train the model with both types of data. So this is different to basically self-rewarding language models that I showed earlier, only had the top part of this picture, right? So it didn't really have an explicit mechanism to improve its ability to evaluate things. And yeah, so this work, I think it's exciting because it helps. We actually get better win rates on, say, alpaca eval with that. And this plot, you can see again, we see the improvement over iterations, but it's above the performance of the self-rewarding model that doesn't have this meta judge training. And even the self-rewarding model tends to plateau a bit here on iteration 4, whereas it's still going up for the meta-rewarding model. So I think that's pretty exciting. And yeah, I've got one more thing to talk about, which is how to improve the chain of thoughts for judgments, for evaluation. So that's another recent work, actually only out last week. So this is called, this work's called Thinking LLM as a Judge. And the goal is to generate these long chain of thoughts similar to O1, R1, but for the task of judgment of responses, again, so that we have good rewards for training our models. So here's an example from the model we trained of what it can do. Outputs this evaluation plan of how it's going to evaluate, and then sort of executes on the plan and gives this final verdict. Yeah, so we have a sort of a training mechanism for that. And the trick here is you can look at the evaluation task actually as a verifiable task if you know which of two responses is better. So let's say you've got an instruction, you've got response A and response B. If you know in advance that A is better or B is better, then that's like a verifiable task, right? Like the math tasks. We can compute the reward directly, right? We don't need say a language model or LLM as a judge to agree, right, with our output. So the trick in this work, the first trick is to generate synthetic evaluation data so that we have verifiable tasks, so we know which one's better. And once we have that verifiable task, we can essentially do something a bit like the iterative reasoning preference optimization, IRPO, because we can compute the rewards directly, right, and build these preference pairs to improve the chain of thoughts for evaluation. There's a couple of extra details here where in this particular case, we actually asked it to do a plan first and then execute on the plan, which is this is the left-hand part of this figure. So how do we create this verifiable data? So this comes from a previous paper we did called Self-Taught Evaluators. What we're going to do is we, given a prompt X, we generate a good response with a language model, or at least we think is a good response. Let's say it's a reasonable response. And then we generate a similar prompt, X prime, which is similar but different to X. And then we also use the LLM, same LLM, to generate a good response to X prime. We'll call that Y prime. And now the hope is that, of course, because X prime is different to X, Y prime won't be as good a response to X, right? So that's the thing, that basically Y should be preferred over Y prime for input X. So this now becomes our verifiable task that we're going to use for training. So the only question there that was a bit of an unknown was how do you make this similar but different prompt? And of course, we use an LLM to do that as well, right? So we say, please generate a modified instruction that's highly relevant but not semantically identical to the instruction above. And then this is what gives us the similar instruction, which we can then generate the lower quality response for the original instruction from. And yeah, that's roughly the higher level picture of this work. There's some ablation studies here where we showed that these plans are superior to not thinking at all, so no chain of thought. But in general, it's good to have the plans as unconstrained as possible. Like if you encourage them to be, for example, lists of criteria or verification questions, which some other works have used with prompting, then the results get worse. And I think that's kind of in line with the O1, R1 style results as well, where basically you don't want to constrain too much the chain of thought thinking processes of these language models, but you want to kind of, train and find out what it's going to be good at. And then, yeah, after we train this model using Llama 3.1 or 3.370B as a base, where it gets very good results. It's actually state of the art on this benchmark called Reward Bench, which evaluates reward models for LLM as a judge, like generative models. And it's also quite good on some harder evaluation tasks on some newer benchmarks that just came out, like RM Bench and Follow Bench eval. And yeah, that's really all the things I'm going to talk about. I think I talked about enough already, right? So just a little bit of a summary of these recent works from the last year. Self-rewarding models, they're models that can train themselves to get better, and the hope is that could be a path to superhuman AI as the model improves itself. We've seen how verifiable rewards can help to train chain of thought for better reasoning. So I showed you this iterative reasoning preference optimization technique, but DeepSeek and O1 have, related techniques, basically all using these verifiable rewards on the output, and then letting the chain of thought kind of don't penalize it, just find ones that work well during your training cycle. And then you can also use these verifiable rewards to improve the evaluation ability of the model. So that's the thinking LLM as a judge that I just showed. And then, of course, if we have these better judges with this chain of thought, the whole thing can go in a cycle, right? We can use those to help train to think on non-verifiable tasks, because we can use this thinking LLM as a judge to train those models, and we call that thinking LLMs, which I showed earlier as well. And then finally, you can use this meta rewarding concept to judge their own judgments as another way of improving their evaluation ability. So I've shown you a few sort of separate papers, but kind of the goal of the bigger model releases try and put some of these ideas together. So yeah, some of those more recent things like meta rewarding and thinking LLMs kind of need to go together with the earlier ideas all in one system, and we'll see how far we can push that. And of course, still looking for new ideas, right? And they're going to be coming in the coming days, weeks, months, and years, I'm sure. So yeah, of course, there's lots of other directions, and just to throw one out there is all the reasoning I've been talking about was with chain of thoughts that were text, right? It's generating text from the language model. Now, you don't have to do that, right? You could, like the transformer itself does reasoning by all these multiplications, inside the neural net. It's all manipulating vectors, right, in the hidden states of the network. And so why does this system 2 reasoning have to be tokens? So maybe that could also be these continuous vectors as well. So we explored that in a recent paper, a method called Coconut, where we replace the chain of thought of like outputting tokens with outputting vectors instead. And we showed that has some promise, actually. It could, say, at least match the performance on some tasks and even outperform classical chain of thought on some more difficult search tasks. But these are all quite small scale tasks, so it remains to be seen sort of how far people can push that direction. I think there's some reasons to want to have the chain of thought in human language, natural language. I think it's a nice thing for safety and interpretability. But as I said, the neural network itself isn't interpretable in that way, right? The internals of the transformer. So that's something we have to work out, I think. And I got another slide about what else comes next? I think there's so much more exciting research to be done. So Ilya Sitskiva, in his Seek-to-Seek paper, Test of Time Award, that was this last NeurIPS talk, he presented some things. This is a picture of what he was saying. What comes next? He was mentioning agents, synthetic data, inference time compute, reasoning, understanding, and being self-aware, which all makes sense. And I think these are all things that, you know, people are working on today. Apart, well, maybe the self-aware one is a little more fuzzy, but the other ones at least. And yeah, I would say that I would just add some more detail there. I think self-improving, self-evaluation is really important because that bottlenecks performance. So using more of this inference time compute for evaluation is only going to help self-improve the model. And I think that's sort of related to this self-aware comment that he makes here, that a self-aware, you know, model might be more able to understand what it knows and what it doesn't know, right? Which is kind of evaluation. And then learning from interaction. I think learning how to reason by actually interacting with people in the world, the internet or itself, are important things. And this sort of that's related to the agents point and the synthetic data point he makes there. And then, of course, it's not just about improving the system 2 reasoning. I think if we can improve system 1 reasoning, so like the transformer architecture itself, then that's great too. So maybe there's a better attention model, some sort of, or maybe something new, a neural network layer we, you know, haven't come up with yet that could change like the scaling laws and the performance of these models, and that's great too. So yeah, plenty to do, and it's going to be exciting to see what happens. Thank you.